Calculus video 25, the quotient rule. So the product rule we use when we had two functions multiplied and we wanted to find the derivative. Likewise, we have the quotient rule, which we'll use whenever we have a function such as h of x is equal to f of x divided by g of x, when we have two functions, one divided by the other, provided that the denominator is not 0. Right, so g of x not equal to 0 here, otherwise we're dividing by 0, and that's a problem. So, for example, let's consider h of x is equal to 2x plus 1 over 3x minus 2. That is a function divided by a function. Sometimes we call this a rational function. This would be an example where we would want to use the quotient rule. Notice that for this particular function, h of x is equal to 2x plus 1 over 3x minus 2, the derivative h prime of x does not exist at x equals 2/3. That's because at x equals 2/3, you were to plug that in the numerator you get, what, 4/3 plus 1, right, 7/3, something like that, divided by the denominator. When you plug in 2/3 into the x in the denominator, you get 3 times 2/3 is 2, minus 2 is 0. That makes you divide by 0. That means the derivative will not exist at x equals 2/3. It will, however, exist everywhere else. All right, so let's talk about the quotient rule. Much like the product rule, where the derivative of two functions being multiplied is definitely not just simply f prime of x times g prime of x. You can't just take the derivative of both functions and multiply them. Similarly, if you have a function h of x equaling f of x over g of x, the derivative is not f prime of x over g prime of x. You cannot simply take the derivative of the top divided by the derivative of the bottom. It does not work that way. So I guess the question is, what does it do? How do you do the quotient rule? So, quotient rule. Let's go, quotient rule. For h of x equaling f of x over g of x, h prime of x is equal to, it's a lot like the product rule. Remember, the product rule is f prime times g plus f times g prime. Okay, reminder, product rule. If you had h of x equals two functions, f of x and g of x, the product rule is h prime of x is equal to f prime of x, g of x, plus f of x, g prime of x. Right? That's the product rule. The quotient rule starts off very similarly. This time our g is the denominator. Just give myself some more room here. H prime of x for the quotient rule is equal to f prime of x, g of x. That's the same starting as the product rule. But instead of plus, it's minus. It's minus f of x, g prime of x. Same as the product rule, except instead of adding, you subtract. But then you have to divide the whole thing by the denominator, g of x squared. So it's f prime of x, g of x, minus f of x, g prime of x, divided by g of x squared. Or f prime g minus f g prime over g squared. That is the quotient rule. We should put a big box around that, star that. That is something we're going to have to know and use quite often. Okay, first let's go with the proof. All right. The proof, if you remember the proof of the product rule, the proof of the quotient rule is similar. When we did the product rule proof, we added and subtracted the same thing, right? And that when you do that, you don't change the problem. And then we use the properties of limits in order to separate them and move them into things that we know, right? These limit definitions of the derivative. That idea is going to be the same when we do the proof of the quotient rule. So let's say, let's do h. Let's say we have a function h of x equaling f of x divided by g of x. And we're trying to prove the quotient rule. So the derivative of h of x is equal to the limit. Look at that, I did it again. I want to say h goes to 0, but I already have an h, so I'm going to go back up here. I'm going to call this capital H. I think I did this the other day. Capital H of x, okay? Now I don't have the same h's. The limit is h goes to 0 of f of x plus h, which in our case, it's both f of x plus h and g of x plus h, right? It's the f of x plus h divided by g of x plus h, minus the function of just x, f of x over g of x, all over h. Okay, so that's how it starts. And like a lot of times we have fractions, the way we work through this is we multiply top and bottom by the common denominator of all the fractions. In this case, the common denominator are the two denominators that we have, g of x plus h and g of x. So that becomes our common denominator, g of x plus h times g of x, and we'll multiply that both on top and on bottom. Doing so, in the numerator, what you're doing is you're picturing g of x plus h times g of x being distributed, right, to both of these things. Both of these terms. When we distribute g of x plus h times g of x to the first term, f of x plus h over g of x plus h, the g of x plus h's cancel. And we get this. This is equal to the limit as h goes to 0. The g of x plus h terms cancel, so I get f of x plus h times g of x. Then minus. On the second blue arrow there, when I distribute g of x plus h times g of x to f of x over g of x, the g of x terms cancel, and we get f of x times g of x plus h. And then in the denominator, we're just going to leave it as h times g of x plus h times g of x. Okay, now you'll notice that if I let h go to 0 at any point in here, the f of x plus h becomes f of x, the g of x plus h becomes g of x, and my numerator then becomes f of x g of x minus f of x g of x, which is 0. And my denominator, the h down there, goes to 0, so 0 times anything is 0, we get 0 over 0. So we're not out of the woods yet. Now we want to do the kind of trick where we add and subtract the same thing. So we want to limit as h goes to 0. Now last time, I believe we added and subtracted, I can't remember if it was f of x times g of x plus h or f of x plus h times g of x. It was one of those two. In this case, last time, when we did the product rule, in this case we have f of x plus h times g of x. We want to subtract f of x times g of x and add f of x times g of x. So we haven't changed anything there, we're just added and subtracted the same thing. And then minus our term from above there, f of x times g of x plus h. Right, so the two terms on the end are the ones we already had. The two terms in the middle are this thing that we created seemingly out of nowhere, where we add and subtract the same thing. Over h times g of x plus h times g of x. All right, now let's see if we can organize this thing. In the first two terms of the numerator, they both have a g of x in common. So we're going to factor out that g of x. In the third and fourth term in the numerator, they both have an f of x in common. We're going to factor out that f of x. It's going to look something like this. The limit as h goes to 0. Numerator, first two terms, we can take out a g of x. We are left with f of x plus h minus f of x. That looks familiar. Plus, third and fourth term, they both have an f of x in common. That will leave me with g of x minus g of x plus h. A little bit less familiar, but somewhat familiar still. Divided by h, g of x plus h, g of x. Okay, When I look at the second term in the numerator, I have an f of x times g of x minus g of x plus h. But we're trying to get this into derivative form, which we know is like f of x plus h minus f of x over h, or if we use the letter g of x plus h minus g of x over h. What we have is g of x minus g of x plus h. Those are backwards. I need the g of x plus h minus the g of x. So to switch it, I'm going to factor out a negative 1. When I factor out a negative 1, the positive g of x then becomes negative. The negative g of x plus h then becomes positive. It looks something like this. That's the limit as h goes to 0 of g of x times f of x plus h minus f of x. Instead of plus, I'm going to factor out a negative 1, so now I have minus f of x times, instead of the negative g of x plus h, I now have positive g of x plus h. Instead of the positive g of x, I now have negative g of x. And that's the form I'm going to want. Over that same denominator. Okay, similar to last time, I'm going to we're dividing this by the same denominator, so I can split that up into two denominators. Or I could also think of this as 1 over, like this denominator, h times g of x plus h times g of x. I could think of this as like 1 over h times 1 over g of x plus h times g of x. If I multiply that together, it's the same thing. In other words, think about it like this. The limit as h goes to 0, that entire numerator, all over h times 1 over g of x plus h, g of x. I didn't change anything, but instead of having this g of x plus h times g of x kind of in the denominator, I'm kind of separating that and multiplying it by 1 over g of x plus h, g of x. This limit as h goes to 0 is still for the whole thing, so I haven't moved it outside of the limit. Now in the numerator, I'm going to separate this into two fractions. So this is the limit as h goes to 0, g of x times f of x plus h minus f of x over h minus, I'll go ahead and separate the limit as well. The limit as h goes to 0, that minus sign comes from that minus sign in the numerator, of f of x times g of x plus h minus g of x over, let's put the over h on that part, times the whole thing times 1 over g of x plus h, g of x. Okay, limit of the whole thing. What we can see now is this. Let all the h's go to 0. Okay, as h goes to 0, I have g of x. The limit as h goes to 0 of g of x is just g of x. The limit as h goes to 0 of f of x plus h minus f of x over h is by definition f prime of x. That is the limit definition of the derivative as h goes to 0. Minus the limit as h goes to 0 of f of x is f of x. The limit as h goes to 0 of g of x plus h minus g of x over h is by definition g prime of x over g of x plus h, as h goes to 0, is just g of x, and then times g of x. That makes g of x squared. And we get, I'm going to switch the order up here, f prime of x, g of x, minus f of x, g prime of x, divided by g of x times itself, which is g of x squared, and we have proven the quotient rule. Okay, very good. It's proven. We can now use it. Let's do some examples and actually use the quotient rule, which is what you'll be doing a lot of. For example, let's start it off with this one. Example 1. Let's say we have a function, I'll call it h of x, is equal to 2x plus 1 over x squared minus 3x. All right, we definitely see this is a quotient. We have to use the quotient rule here. Remember that it is not. You cannot simply take the derivative of the top and get 2, and the derivative of the bottom and get 2x minus 3 and call it a day. Can't do it. You have to use the quotient rule. You should write out the quotient rule as much as you possibly can to help you remember it. H prime of x will be f prime of x. That's f being the numerator and g being the denominator. F prime of x, g of x, minus f of x, g prime of x, like the product rule, but with a minus sign in the middle, divided by g of x squared. Right, that is the quotient rule. So let's use it. So I want f prime, I want the numerator prime. The derivative of the numerator is the derivative of the numerator. 2x plus 1 is my numerator. Its derivative is just 2. Times g of x. So times the original g of x, the original denominator, not the derivative of the denominator, just what is the denominator, x squared minus 3x. And then minus, we will leave the numerator, f of x, leave the 2x plus 1 all by itself, it is there, the whole thing, times the derivative of g, times the derivative of the denominator, which is 2x minus 3. Divide that whole thing by the denominator squared. And that is the quotient rule, but we're not done. When you're doing the quotient rule, you want to be able to simplify if possible, and you can often simplify these. So what we're going to do is we're going to distribute within the numerator. We're going to take the 2 times the x squared, the 2 times the negative 3x. We're going to distribute here, right, in like a foiling kind of thing. Remembering to subtract all those terms. We're going to subtract that FOIL. So I'm going to put that FOIL, that 2x plus 1 times 2x minus 3, that distribution in parentheses. It's going to look something like this for our simplification. 2 times x squared is 2x squared. 2 times negative 3x is negative 6x. Minus, parentheses. 2x times 2x is 4x squared. 2x times negative 3 is negative 6x. 1 times 2x is 2x. 1 times negative 3 is negative 3. All still divided by x squared minus 3x squared. Okay, let's see, let's combine some like terms. So we have 2x squared minus 6x minus parentheses 4x squared. We have the negative 6x and the 2x, which makes negative 4x minus 3. Nothing else changed there. Just combine those two terms that were underlined. Then we'll go ahead and distribute that negative sign, right, on that second part there that's in parentheses. So we have 2x squared minus 6x minus 4x squared plus 4x plus 3. That negative sign, right, going to all three of those terms. Divided by, same thing, x squared minus 3x all squared. Now let's see if anything will combine. We have a 2x squared minus 4x squared, that is negative 2x squared. A negative 6x and positive 4x is minus 2x, and a plus 3. Divided by x squared minus 3x squared. Now if you box this answer and said this is what my answer is, I would give you full credit for that. But I don't like the leading coefficient of my numerator to be negative, so in order to make it seem more appealing to me, I'm going to factor out a negative. That will leave me with positive 2x squared plus 2x minus 3 divided by x squared minus 3x squared. And take a quick check. Make sure that numerator doesn't factor. It doesn't in this case, but check it out to be sure. That way, in case something might cancel out with the denominator term. In this case, it does not. And so you are done. Quotient rule. This is the derivative. This is h prime of x. All right, very good. Let's try at least a couple more here. How about h of x is equal to 5x squared plus x, 5x squared plus x divided by 2x minus 4. And go ahead, pause the video, try the quotient rule. If you get stuck, come back and watch. All right, we're going to think of this as the numerator is f of x, denominator g of x, therefore h prime of x, just writing out the quotient rule again. F prime of x, the derivative of the top times the denominator, minus the top function times the derivative of the denominator divided by the denominator squared. Okay, so for us, it'll look like this. H prime of x is the derivative of the numerator. The derivative of 5x squared plus x is 10x plus 1 times the g of x times the denominator 2x minus 4 minus f of x. We're leaving the numerator as 5x squared plus x, that's our f of x function, times g prime. The derivative of 2x minus 4 is just 2. All divided by 2x minus 4 squared. Now, that is technically the derivative, but we want to simplify this, so we're going to distribute the 10x times the 2x, the 10x times the negative 4, the 1 times the 2x, the 1 times the negative 4, and then on the right over there, distribute the 2 into both of those terms. So this is equal to 20x squared minus 40x plus 2x minus 4 minus, parentheses, 10x squared plus 2x, distributing the 2 into those terms, over 2x minus 4 squared. So we have, let's see, I can see that the negative 40x and the positive 2x will combine for negative 38x. So we have 20x squared minus 38x minus 4. Minus 10x squared, right, distributing that negative sign, minus 2x over 2x minus 4 squared is equal to 20x squared minus 10x squared. That sounds like 10x squared. Negative 38x minus 2x is negative 40x, and then minus 4. All right, 10, 40, and 4 will all divide by 2, so let's make sure this thing won't factor. 5x squared minus 20x minus 2 divided by, okay, 2x minus 4 squared. You could think of that as 2 times x minus 2, right? That would be 2x minus 4, the whole thing squared. So if I'm squaring the whole thing here, I'm squaring both the 2 here and I'm squaring the x minus 2. 2 squared is 4, x minus 2 squared is x minus 2 squared. So this is 2. 5x squared minus 20x minus 2 over 4 times x minus 2 squared. The 2 and the 4 cancel out, the 4 becoming a 2. Looking at the 5x squared minus 20x minus 2, see if it factors. It doesn't. Nothing is going to multiply to negative 10 and add to negative 20. Therefore, our final answer is this. 5x squared minus 20x minus 2 divided by 2 times x minus 2 squared. Quotient rule. That's h prime of x. Okay, one more, and then we will call done for this video. Let's say h of x is equal to 3e to the x over e to the x plus 3. Please do not cancel out those e to the x's. The denominator is e to the x plus 3, therefore you can't simply cancel that e to the x with an e to the x on top. Please do not do that. Our function here, f of x on the numerator, or g of x in the denominator. So our derivative, h prime of x, just writing it out, the more times you write it, the easier it becomes. There you go. F prime of x, g of x, known as f of x, g prime of x over g of x squared. So we're looking for the derivative of the numerator. So h prime of x, the derivative of the numerator, 3e to the x, its derivative is itself, 3e to the x. That is the derivative of the numerator. That is f prime. Times g, which is e to the x plus 3. Minus, leave the original top function, 3e to the x, that's just f of x, times g prime. The derivative of e to the x is e to the x, but the derivative of the plus 3 part, the derivative of the constant 3 is 0. So we just get e to the x divided by e to the x plus 3 squared. Okay, let's do some distribution and see where we're at. Side note, this is important. We'll use this kind of property of exponents quite often. If I have e to the x times e to the x, that is by definition e to the x squared, right? Same two things multiplied together. 4 times 4 is 4 squared. This is e to the x squared. By properties of exponents, remember that a to the m to the n is equal to the a to the mn, where you could multiply those two, which is also equal to a to the n to the m. Those can actually switch. We're not switching it in this case. We are simply going to multiply the two together. My side note needed to be bigger. All right, so we had this property, right? This is a property of exponents here. We're going to use that to say that e to the x squared is the same thing as e to the multiplying x times 2 is 2x. E to the x squared is equal to e to the 2x. Maybe kind of make a note of that. It's useful for us. So simplifying, doing some distribution here, 3e to the x times e to the x, 3e to the x times 3, and then on the right over there, 3e to the x times e to the x. We get 3e to the x squared, or 3e to the 2x, plus 9e to the x. That's 3e to the x times 3. Minus, on the right over here, we get 3e to the x times e to the x. That's 3e to the x squared, or just e to the 2x, divided by e to the x plus 3 quantity squared. Now we see that 3e to the 2x here, the first term, minus 3e to the 2x, the last term, cancel out, leaving us with 9e to the x divided by e to the x plus 3 squared. And that is h prime of x.